Welcome back to Sleep Science Studio. I am your guide, Thomas, and it is a distinct pleasure to have you with us tonight. Here, we believe that understanding the universe, in its quiet and intricate detail, is one of the most profound pathways to deep and restorative rest. We trade the anxieties of the day for the quiet wonder of the cosmos, allowing complex ideas to become a gentle, intellectual hum in the mind. Our purpose here is not to keep you awake with startling facts, but to provide a soft place for your mind to land. Consider this a sonic blanket, woven from the fundamental threads of physics, astronomy, and the deep, silent rhythms of the universe. Tonight, we will embark on a quiet journey together, exploring a connection that binds our world to the silent satellite that circles above. We are going to explore the gentle, yet immensely powerful, relationship between the moon and the Earth's vast and restless oceans. It is a story of gravity, of resonance, and of a cosmic dance that has been unfolding for billions of years, a rhythm that continues now. So let this be the last thing your conscious mind focuses on tonight, a final, fascinating thought to carry you into sleep. Let the intricate science of the tides become a gentle lullaby, a story of immense forces moving in perfect, predictable harmony. I often wonder where you might be listening from, in your particular corner of the world, under your specific patch of night sky. Perhaps you are in a bustling city, where the stars are washed out by a gentle glow of artificial light, a soft, urban nebula. Or maybe you are somewhere far more remote, where the Milky Way is a brilliant, shimmering band painted across the darkness. Whatever your location, the same moon that we will discuss tonight is likely somewhere in your sky, or just below your horizon. It might be a brilliant full disk or a delicate, almost invisible sliver of a crescent, but its influence remains constant. And I wonder what time it is for you. Is it just after dusk, as the world settles into its nocturnal rhythm? Or perhaps it is much later, in those quiet, liminal hours just before dawn, when the world is at its most still. Regardless of your time or place, we are connected now by this shared experience, this moment of quiet learning and relaxation. You are now a part of the Sleep Science Studio community, a collective of curious minds seeking rest through understanding. It is an honor to be your guide on this particular evening as we prepare the mind for its own nightly journey into sleep. As we continue, if you find this experience valuable, a simple click of the like button is a quiet and wonderful way to show your support. It helps our studio reach other minds who may be searching for this unique blend of scientific exploration and deep, calming rest. And if you wish to join us for future explorations, consider subscribing to Sleep Science Studio and becoming a permanent part of our community. There is no pressure, of course. The most important thing is your comfort and your gradual drift towards a peaceful state of mind. Our primary mission, after all, is to help you sleep, so I must confess, I hope this isn't too interesting for you. I hope the concepts are just interesting enough to hold your attention gently, without demanding too much of your cognitive energy tonight. Think of it as a mental massage, where the ideas are firm enough to be felt, but gentle enough to soothe and relax. So please, do not feel the need to memorize any of this. Simply allow the words and concepts to wash over you. The goal is not retention, but relaxation. The purpose is not examination, but a gentle, intellectual, and emotional release. Let the rhythm of the science and the cadence of my voice be your anchor as you drift away from the shores of wakefulness. And now for our standard disclaimer. I am not a medical professional, and this content is not intended to be a substitute for professional medical advice. This channel is designed for educational and relaxation purposes only, a form of intellectual comfort food for the curious and tired mind. If you have persistent sleep issues, please consult with a qualified healthcare provider who can address your specific, individual needs. Our role here is simply to provide a serene and intellectually stimulating environment conducive to the natural process of falling asleep. Now is the time to finalize your preparations for rest. Find that perfect position, the one where your body feels most at ease. Allow your muscles to release any tension they might be holding from the day. Feel the weight of your body supported completely. Notice the gentle coolness of the air on your skin. and the subtle rhythmic motion of your own breathing, in and out. This breath is your own personal rhythm, a biological constant that connects you to the great rhythmic cycles of the universe we are about to explore. Let each exhalation be a release, a letting go of the day's concerns, making space for a deep and profound sense of tranquility. You are in a safe place, a place of quiet curiosity, and you have done everything you need to do for today. Our quiet journey tonight begins with a simple observation. The ocean's surface is not still. It rises and falls with a profound and reliable rhythm. This is the tide, a planetary-scale breath drawn in and out twice each day, a phenomenon so familiar we often forget to marvel at it. But what is the engine driving this immense movement of water? The answer lies not on Earth, but hundreds of thousands of miles away. It lies with our silent cratered companion, the Moon, hanging in the velvet blackness of space, locked in a gravitational embrace with our world. The connection is gravity, a force we experience every moment, yet one whose subtle complexities orchestrate this grand oceanic spectacle. So, let us begin our exploration there, with the fundamental nature of this invisible tether that binds worlds together across the void. We will travel from the core of the Earth to the surface of the Moon to understand how this force can reach across space to move an ocean. Settle in and let your mind drift. We are about to peel back the layers of the familiar to reveal the strange and beautiful mechanics beneath. This is the story of the tides, a story of a deep and ancient connection written in the language of physics and time. And our story begins, as all stories of celestial mechanics must, with the quiet, persistent, and universal force of gravity. Isaac Newton first codified our understanding of this force, proposing that every object with mass in the universe exerts a gravitational pull on every other object with mass. It is not a property of special celestial objects alone. It is a fundamental quality of existence. The chair you are sitting in, the book on your table, your very body, each exerts a tiny, imperceptible gravitational field. It is only when we consider objects of immense mass, like a planet or a moon, that this force becomes a dominant architect of motion, capable of holding worlds in orbit and, as we shall see, moving the very oceans upon them. This gravitational force is intrinsically tied to two key variables, mass and distance. The more massive an object, the stronger its gravitational pull. A star like our Sun, for instance, holds all the planets of our solar system in its grasp due to its immense mass. But just as important is the role of distance. The force of gravity diminishes significantly as two objects move farther apart. This relationship is not linear. It follows what is known as an inverse square law, meaning that if you double the distance between two objects, the gravitational force between them drops to just 1/4 of its original strength. This rapid weakening with distance is the critical secret to understanding the tides. Now, let us apply this principle to the Earth and the Moon. The Moon, though much smaller than the Earth, is massive enough and close enough to exert a considerable gravitational pull on our planet. It is this pull that keeps the Moon in its stable orbit, a constant cosmic companion. But it is a mistake to think of this pull as a single, uniform force acting on the entire Earth at once. Because the Earth is a vast, spherical body, nearly 8,000 miles in diameter, different parts of our planet are at slightly different distances from the Moon at any given moment. And in that slight difference, the entire phenomenon of the tides is born. This concept is known as a differential gravitational force, or more simply, a tidal force. It is the difference in the Moon's gravitational pull across the diameter of the Earth. The side of the Earth that is currently facing the Moon is closer, and therefore it experiences the strongest pull. The very center of the Earth, its core, experiences an average pull. And critically, the side of the Earth facing directly away from the Moon is the farthest, and so it experiences the weakest pull. This stretching or elongating effect, caused by the variance in gravitational attraction, is the true engine of the tides. Imagine the Earth not as a solid, rigid ball, but as a slightly deformable sphere, wrapped in a thin, fluid layer of water, our oceans. The solid body of the Earth is relatively rigid and moves as one unit in response to the Moon's average gravitational pull on its center. The oceans, however, are liquid and are free to move and respond to these subtle differences in force. This is the key. The tides are not about the Moon lifting the entire ocean. They are about the Moon reshaping the ocean by pulling on near, middle, and far parts of the Earth with slightly different strengths, creating a subtle disfigurement in the sphere of water. Let us first focus our attention on the side of the Earth closest to the Moon. On this near side, the liquid water of the oceans is being pulled by the Moon's gravity more intensely than the solid Earth beneath it. Think of it as a race. The water is being pulled forward more vigorously than the land. Because of this stronger attraction, the water begins to move, creating a bulge, a piling up of water that we experience as a high tide. This is the most intuitive part of the tidal mechanism, the direct gravitational attraction on the water closest to our lunar neighbor, creating what is known as the sublunar tidal bulge. This bulge is not a wave traveling across the ocean in the conventional sense, like a ripple from a stone. It is more accurate to think of the entire ocean itself being reshaped into a slightly oblong or football-like shape. The Earth then rotates beneath this elongated shape of water. So when you are standing on a coast and the high tide arrives, you are not watching a wave come in. Rather, your specific location on the spinning Earth is being carried into this pre-existing bulge of water that is held in place by the Moon's persistent gravitational influence. It is a subtle but profound distinction in perspective. Now, we must turn our attention to the great counterintuitive mystery of the tides, the part of the story that truly reveals the strangeness of gravitational physics. We have accounted for one high tide, the one on the side of the Earth facing the Moon. But as anyone who has spent time by the sea knows, there are typically two high tides each day. If the Moon is pulling the water towards it, how can there possibly be a second high tide on the exact opposite side of the planet, the side facing away from the Moon into the deep of space? The answer lies back within that same concept of differential forces. The second bulge is not created by a pulling force, but rather by the lack of one. On the far side of the Earth, the water in the ocean is the furthest it can be from the Moon. Here, the Moon's gravitational pull is at its absolute weakest. The solid body of the Earth, being closer to the Moon, is pulled away from the water on the far side. In essence, the Earth is pulled towards the Moon more strongly than the water on the far side is, and that water is effectively left behind, forming a second, opposite bulge. This is a beautiful piece of cosmic symmetry. On the near side, the water is pulled away from the Earth. On the far side, the Earth is pulled away from the water. In both cases, the result is the same, a separation between the ocean's surface and the solid planet, creating a bulge. One bulge is caused by a direct pull, and the other is caused by being left behind. This second bulge is known as the antipodal tidal bulge. Together, these two bulges, locked in alignment with the Moon, create the planet-wide distortion in our oceans that governs the rhythm of the tides. So let us picture this system in its entirety, a quiet and elegant dance. We have the Earth, a sphere, and we have the Moon, its constant partner. The Moon's gravity stretches our planet's oceans along the Earth-Moon line, creating two bulges. One bulge points directly towards the Moon, and the other points directly away from it. These bulges remain more or less aligned with the Moon as it orbits the Earth. The solid Earth, however, is spinning on its axis much more rapidly, completing a full rotation roughly once every 24 hours. This rotation is what creates the daily experience of the tides. As your particular spot on the globe spins, it journeys into the first bulge, and the sea level rises. This is your first high tide. Hours later, as the Earth continues to turn, your location moves out of that bulge, and the sea level falls. This is the subsequent low tide. Then, your journey continues as you're carried into the second bulge on the opposite side of the planet. bringing the second high tide. Finally, you rotate out of that second bulge and back into a low tide zone, completing the cycle. It is the Earth's rotation, not the Moon's motion, that causes the twice-daily rise and fall along our coastlines. This explains the fundamental rhythm. But the story has another layer of complexity, another celestial body whose influence we must consider: the Sun. The Sun is vastly more massive than the Moon, about 27 million times more massive, in fact. Its gravitational pull on the Earth is therefore immense, far stronger than the Moon's. However, the Sun is also about 400 times farther away from us than the Moon is. And because tidal forces are born from the difference in gravity across an object, and that difference weakens rapidly with distance, the Sun's tidal effect on Earth is actually less than half that of the Moon. Despite being weaker, the Sun's tidal influence is still significant. It creates its own pair of tidal bulges on the Earth, aligned with the Sun. These solar tides are smaller than the lunar tides, but they interact with them in predictable and fascinating ways. The overall height of the tide on any given day depends on how the solar bulge and the lunar bulge are aligned. Sometimes they work together, amplifying each other, and sometimes they work against each other, dampening the effect. This celestial interplay creates a monthly cycle of stronger and weaker tides. When the Sun, the Earth, and the Moon are all aligned in a straight line, which happens during the new moon and the full moon, their gravitational forces combine. The solar tidal bulge stacks on top of the lunar tidal bulge. This constructive interference leads to the most extreme tides of the month. The high tides are higher than average, and the low tides are lower than average. These are known, somewhat poetically, as spring tides. The name has nothing to do with the season. It comes from the old German word springen, meaning to leap up. Conversely, when the Moon is in its first or third quarter, it is at a right angle to the Sun relative to the Earth. During these phases, the gravitational pull of the Sun is working against the gravitational pull of the Moon. The Sun's tidal bulge is creating a high tide in the location where the Moon's influence is creating a low tide. They are out of sync. This destructive interference cancels out some of the tidal force, leading to the least extreme tides of the month. The high tides are not very high, and the low tides are not very low. These are called neap tides. This monthly cycle from springtide to neap tide and back again is a beautiful and direct manifestation of our solar system's geometry. It is a rhythm written in the very fabric of space-time, visible in the waters of our own planet. The slow, patient dance of the Sun, Earth, and Moon is reflected in the gentle lapping of the waves on every shore. It is a reminder that we live within a dynamic and interconnected system, where the movements of distant worlds have tangible effects right here at home in the most familiar of natural cycles. The story, however, does not end with these perfect, symmetrical bulges. The reality of tides on Earth is far more complicated, because our planet is not a smooth, water-covered sphere. The continents get in the way. The shape of the ocean floor, the presence of islands, and the contours of coastlines all serve to disrupt and modify the flow of these tidal bulges as the Earth spins. The two great tidal bulges are the underlying theoretical force, but the actual tides we experience are a complex product of this force, interacting with the planet's unique and varied geography. Think of the tidal bulge as a very long, planetary-scale wave, with a wavelength thousands of miles long. As this wave attempts to travel around the spinning globe, it is blocked, channeled, and reflected by the land masses. In the open ocean, the tidal range might be only a few feet. But when this tidal energy is funneled into a narrow bay or a constricted channel, the water can be forced to pile up dramatically. The shape of the land acts as a natural amplifier, turning a modest oceanic tide into a spectacular rise and fall of the sea. This is why the height of the tides varies so enormously from place to place. A small, enclosed sea like the Mediterranean experiences almost no tidal variation, as the water cannot easily flow in and out to form a significant bulge. In contrast, a place like the Bay of Fundy in Canada, with its unique funnel shape and length, experiences the highest tides in the world. The bay's natural resonance frequency happens to align perfectly with the tidal cycle, allowing the incoming water to slosh back and forth, building in height with each cycle until it reaches staggering levels of over 50 feet. There is another subtle but profound consequence of this immense movement of water, a consequence that plays out not over hours or days, but over eons. As the Earth spins, it effectively drags the tidal bulges with it, slightly ahead of the Earth-Moon line. The continents rotating eastward try to pull the ocean along, while the Moon's gravity tries to pull the bulges back into alignment. This creates a vast amount of friction between the moving ocean and the seabed. This is known as tidal friction, and it acts as a very gentle but very constant brake on our planet. This constant braking, this tidal friction, has been slowing down the Earth's rotation for billions of years. The energy that is lost from the Earth's spin doesn't just disappear, it is transferred to the Moon's orbit. According to the law of conservation of angular momentum, as the Earth slows down, the Moon must speed up, and in doing so, it slowly spirals away from us. Billions of years ago, a day on Earth was much shorter, perhaps only 6 hours long, and the Moon was much, much closer in the sky, appearing far larger than it does today. Measurements confirm this is still happening. The length of an Earth day is increasing by about 1.8 milliseconds every century. It is an imperceptible change on a human timescale, but a profound one on a geological timescale. And the Moon is drifting away from us at a rate of about 3.8 centimeters, roughly the speed at which your fingernails grow, every single year. The very rhythm of our day and the distance to our nearest celestial neighbor are being actively shaped by the sloshing of water in our oceans, a quiet and patient geological force of immense consequence. So the tides are more than just a simple rising and falling of the sea. They are the physical manifestation of a gravitational conversation between the Earth, the Moon, and the Sun. They are a story of differential forces stretching our world, of a spinning planet moving through oceanic bulges, and of a complex interplay with geography that creates infinite local variations. They are a brake on our planet's rotation and an engine pushing our Moon ever so slightly farther away, a process that has been unfolding since the oceans first formed and will continue for eons to come. The next time you have the chance to stand by the ocean, take a moment to consider the sheer scale of what you are witnessing. The water that recedes from your feet is responding to an invisible tether, a gravitational gradient stretching across more than 200,000 miles of empty space. You are observing a local effect of a truly planetary phenomenon, a rhythmic pulse that connects the solid ground beneath you to the silent, cratered world hanging in the sky. It is a quiet, reliable miracle of celestial mechanics, playing out in perfect time, day after day. Let's return once more to the core concept of the two bulges, for it is here that the deepest understanding lies. The sublunar bulge, the one facing the Moon, is a testament to direct force. The water molecules here are simply more attracted to the Moon's mass than is the Earth's center. This is the part of the tide that feels most logical, a straightforward consequence of gravity's pull. It is an affirmation of the simple principle that proximity increases attraction, a rule that governs everything from orbiting planets to the clustering of galaxies across the vast expanse of the cosmos. This direct pull is not uniform across the bulge itself. Even within this single bulge of water, there is a gradient. The water at the point on the Earth's surface directly beneath the Moon is pulled the very strongest. The water on the periphery of that bulge is pulled slightly less strongly and at a slightly different angle. This complex field of vectors is what shapes the gentle curve of the high tide, a smooth and subtle mountain of water, trillions of tons in mass, held in place by an invisible and silent force, a testament to the cumulative power of infinitesimal differences. It is a quiet marvel that a body as far away as the Moon, a world with no atmosphere, no life, no sound, can reach out with its invisible gravitational hand and so profoundly affect the liquid surface of our own vibrant planet. It speaks to the universal nature of physical law, the fact that the same rules that govern a falling apple or a thrown stone are also responsible for orchestrating this immense planetary-scale movement. The science of the tides connects the mundane to the magnificent, showing them to be two sides of the same elegant and unified reality. Now let us revisit the far side of the Earth, the place of the second, more mysterious bulge. The antipodal bulge is a lesson in relativity, not in the Einsteinian sense, but in the simple mechanical sense that all motion is relative. The water on the far side is not being pushed away, nor is it subject to some strange repulsive force. It is simply that its frame of reference, the solid Earth, is being pulled away from it. It is an act of cosmic subtraction. The Earth is pulled by X amount, the far water is pulled by Y amount, and X is greater than Y, leaving the water behind. This concept of being left behind by gravity is not unique to our tides. It is a key principle in understanding how certain star clusters are shaped, or how galaxies can be stripped of their gas as they pass through dense regions of intergalactic space. The parts of an object that are more weakly bound by gravity can be left behind when the object as a whole is accelerated. The second tidal bulge is a perfect, local demonstration of a process that sculpts structures on a galactic scale. Our oceans are a gentle laboratory for the great forces that shape the universe. The presence of these two opposing bulges is what establishes the fundamental semi-diurnal rhythm of the tides, the pattern of 2 high tides and 2 low tides per day, experienced by most coastlines on Earth. If there were only one bulge, we would only experience 1 high tide each day as we rotated into it. But the beautiful symmetry of differential gravitation, creating a bulge by pulling and a bulge by leaving behind, doubles this frequency. It is an elegant solution that ensures a balanced, rhythmic distribution of tidal energy across the planet. As you rest now, you can imagine yourself on this rotating sphere. In your mind's eye, see it turning slowly and smoothly through these two vast invisible fields of force. Feel the gentle rise as you are carried into the crest of a tidal bulge, and the slow fall as you descend into a trough. This is a rhythm that has been part of our planet for billions of years, a deep and abiding metronome ticking away the geological ages. It is a rhythm that is embedded in the life cycles of countless marine organisms, a clock set not by the sun but by the moon. Consider the sheer volume of water being moved in this process. The oceans hold over 300 million cubic miles of water, and a significant fraction of this mass is being constantly reorganized by the moon's tidal pull. The amount of energy involved in this daily redistribution is astronomical, dwarfing all human endeavors combined. It is a quiet, gentle display of power on a scale that is difficult to comprehend, yet it happens with such reliability and subtlety that we can easily take it for granted, like the rising of the sun. The solid Earth itself is not perfectly rigid, and it too experiences a tide. The same differential forces that create the ocean tides also stretch and deform the planet's rocky crust. This body tide is much smaller, causing the ground beneath your feet to rise and fall by several inches each day. We do not perceive it because everything around us, including our measurement devices, rises and falls with it. But it is there, a constant, silent flexing of the entire planet in response to the moon's gentle, persistent gravitational tug. Even the atmosphere is subject to a tide. Just as with the oceans and the solid Earth, the blanket of air surrounding our planet is stretched into 2 bulges by the moon's gravitational field. This atmospheric tide is a very subtle effect, causing tiny fluctuations in surface barometric pressure. It is mostly masked by the much larger pressure changes caused by weather and daily heating from the sun. But with sensitive instruments, this lunar signature can be detected, another layer to the complex, multifaceted influence of our silent satellite. So the tidal force is a universal phenomenon affecting every part of our planet, liquid, solid, and gas. The ocean tides are simply the most dramatic and visible manifestation, because water is so much more free to move than rock. When we watch the tide come in, we are seeing the most obvious part of a much deeper process, a total planet reshaping that occurs on a twice-daily basis. It is a holistic response of our world to the gravitational environment in which it resides, a constant state of gentle, rhythmic distortion. This process of tidal stretching is not always so gentle. If a smaller object, like a comet or a moon, gets too close to a much larger planet, the tidal forces can become extreme. The differential pull on the near side versus the far side can become stronger than the object's own gravity that is holding it together. At a certain point, called the Roche limit, the tidal forces will overwhelm the object's internal cohesion and tear it apart, often forming a beautiful ring system like the one we see around Saturn. The rings of Saturn may well be the remnants of a moon that strayed too close. Our own moon is safely outside Earth's Roche limit, so it is in no danger of being torn apart. Instead, it is locked in this far more gentle and in many ways more complex tidal relationship. A relationship that does not destroy, but instead creates a rhythm. A relationship that slows our planet's rotation over eons and gently pushes the moon itself away. It is a stable, enduring, and creative interaction, one that has shaped the evolution of life on Earth by creating intertidal zones, and has possibly even influenced the planet's long-term climate through its effect on ocean mixing. The double bulge is the key to it all. It is a concept that requires a slight shift in our thinking, away from a simple idea of pulling and towards a more nuanced understanding of gravitational stretching. Once you grasp this idea, that the ocean bulges on the near side because it is pulled away from the Earth, and on the far side because the Earth is pulled away from it, the entire system clicks into place. The two high tides a day are no longer a mystery, but an elegant and logical consequence of universal physical laws. As you prepare to drift into a deeper state of relaxation, allow this image to settle in your mind. A beautiful blue planet, spinning smoothly in the darkness. Wrapped around it, a slight, invisible distortion in the shape of its oceans, an elongation held in place by its distant, loyal moon. Everything else, the lapping of waves, the monthly cycle of spring and neap tides, the very length of our day, is just a detail emerging from this simple, silent, and profoundly graceful astronomical arrangement. Let's linger on this far side bulge, the antipodal bulge, for just a moment longer. It is perhaps the most elegant piece of the puzzle. It requires us to abandon the perspective of standing on the Earth and instead adopt a more objective, external viewpoint. From this vantage point in space, we can see the moon pulling on every single particle of the Earth system. It pulls strongest on the near-side ocean, less strongly on the solid Earth, and least strongly of all on the far-side ocean. The result is a sorting, a separation based on distance. This sorting process is a beautiful illustration of inertia. Inertia is an object's resistance to a change in its state of motion. The water on the far side of the Earth has inertia. It wants to continue on its path. As the solid body of the Earth is accelerated slightly more towards the moon, the far side water resists this change. It is this inertial resistance, this tendency to be left behind, that allows the second bulge to form. It is not an active force, but a passive consequence of existing in a dynamic, accelerating frame of reference. The symmetry of this outcome is deeply satisfying from a scientific perspective. Nature often exhibits such balances. The forces may be different, a direct pull on one side and inertial lag on the other, but the resulting shape is balanced and symmetrical. This duality is a common theme in physics, from particles and antiparticles to the positive and negative poles of a magnetic field. The tides are another example of this fundamental harmony, a planetary scale expression of equilibrium and balance in the face of external forces. It is a wonderful thought to hold as you drift towards sleep, that even in the vastness of space, there is a kind of logic and fairness. The side of the world bathed in moonlight receives its high tide, a direct gift from our lunar companion. But the side of the world turned away, facing the cold emptiness of deep space, is not forgotten. It receives its own high tide in equal measure, a gift born not of presence but of a subtle and relative absence. a perfect balance is maintained. This entire elegant mechanism proceeds in utter silence. There is no sound of immense gravitational forces, no roar of a planet being stretched. The only sounds are the ones created when this silent cosmic wave meets the land, the gentle breaking of waves on a sandy beach, or the crash of surf against a rocky cliff. These are the final, audible expressions of this immense and silent dance that began hundreds of thousands of miles away, a conversation between worlds translated into the soothing, rhythmic language of the sea. Understanding this process does not diminish its magic. It enhances it. To know that the rhythm of the ocean is tied to the orbital mechanics of the moon enriches our experience of the natural world. It transforms a simple observation into a moment of connection with the cosmos. It reminds us that our world is not an isolated system, but an active participant in the grand, gravitational ballet of the solar system. We are tied to the heavens by invisible, powerful, and wonderfully predictable forces. So as you lie here, feeling the gentle rise and fall of your own chest, know that the oceans are performing a similar breath. On a much grander scale, your personal, biological rhythm is mirrored in the geological and astronomical rhythm of the planet itself. It is a slow, deep, and steady breath, drawn in and released over hours, orchestrated by the silent passage of the moon across the sky. Allow your own breathing to sync with this imagined planetary rhythm, finding a deep and profound sense of calm in this shared universal pulse. The two bulges, then, are the foundation of it all. One is a bulge of attraction. The other is a bulge of inertia. Together, they create the oblong shape, the elongated sphere of water that our spinning Earth turns through. They are the twin pillars upon which the entire science of the tides is built. A simple concept of differential gravity, creating a beautifully complex and endlessly fascinating natural phenomenon that has captivated human curiosity for millennia, and will continue to do so for as long as the moon graces our sky. Let this knowledge be a source of intellectual comfort. The world is not chaotic. Beneath its sometimes turbulent surface, there are deep, abiding, and understandable principles at work. The tides are a perfect example. They are a complex system, yes, but they are not random. They are governed by laws that are as reliable as the dawn. There is a profound reassurance in this predictability, a sense of stability in knowing that these great forces are moving in a harmony that can be understood, appreciated, and used as a final, fascinating thought to guide you into rest. The story is not quite over. We have established the primary players, the Earth's rotation and the two tidal bulges created by the moon, gently modulated by the sun. But now we must consider the finer details of this interaction. What happens when the rhythm of the tides meets the complex friction of the real world? The consequences are subtle, playing out over geological time, but they are profound, altering the very relationship between the Earth and the moon. It is a story of energy, friction, and the slow, inevitable transfer of cosmic momentum. Let us now delve deeper into this concept of tidal friction, the gentle yet relentless break that has been shaping the relationship between our world and its moon for billions of years. The origin of this friction lies in a simple mismatch of speeds. The Earth rotates on its axis once every 24 hours, a dizzying speed when viewed from a celestial perspective. The moon, however, orbits the Earth far more slowly, taking roughly 27 days to complete one circuit. This discrepancy is the source of all the long-term changes we are about to explore. The fast-spinning Earth is constantly trying to outrun the slow-orbiting moon's gravitational influence. Because the Earth is spinning faster than the moon is orbiting, the solid body of the planet attempts to drag the two tidal bulges along with it. The continents and the friction of the water against the vast, uneven terrain of the ocean floor pull the watery bulges slightly forward in the direction of the Earth's rotation. The moon's gravity, in contrast, is constantly trying to pull these bulges back into perfect alignment with the Earth-Moon line. The result is a compromise, a dynamic equilibrium. The tidal bulges do not sit directly under the moon, but are dragged slightly ahead of it. This slight offset, this leading bulge, is of monumental importance. Imagine the Earth and its two bulges from the moon's perspective. One bulge is slightly closer to the moon, and one is slightly farther away, but they are no longer in a perfect line. The closer, leading bulge now has a gravitational pull of its own, and because it is slightly ahead of the moon, it tugs the moon forward in its orbit, constantly urging it to speed up. It is like a gravitational tow rope, pulling the moon into a slightly faster orbital path, a tiny but constant acceleration. Conversely, the moon pulls back on this leading bulge of water. It is a gravitational tug-of-war. The moon tries to pull the bulge back into alignment, and this backward pull on the ocean acts against the Earth's rotation. This is the very essence of the tidal break. It is an immense planet-scale friction caused by the moon's gravity trying to slow down the ocean that the spinning Earth is trying to speed up. The energy dissipated in this process, mostly as a tiny amount of heat in the oceans, is colossal, but spread over such a vast area that it is imperceptible. This process is governed by one of the most fundamental laws of physics, the conservation of angular momentum. In a closed system, like the Earth and Moon, the total amount of angular momentum, which is essentially the momentum of rotation, must remain constant. It cannot be created or destroyed, only transferred from one part of the system to another. The Earth-Moon system contains two primary reservoirs of this momentum, the fast spin of the Earth and the slower orbit of the Moon around the Earth. The tidal friction is the mechanism that facilitates the transfer between these two reservoirs. As the tidal break slows the Earth's rotation, our planet is losing angular momentum. But that momentum cannot simply vanish. It has to go somewhere. The energy is transferred via the gravitational pull of that leading tidal bulge directly to the Moon. The Moon absorbs this angular momentum, which has a very specific and perhaps counterintuitive effect on its orbit. Gaining angular momentum does not make the Moon fall towards the Earth. It does the opposite. It pushes the Moon into a higher, larger, and more distant orbit. A strange and beautiful cosmic exchange. This is a fundamental principle of orbital mechanics. If you want to move a satellite to a higher orbit, you fire its thrusters to make it go faster. This increase in speed causes it to climb into a wider, more energetic orbit. The leading tidal bulge acts as a constant, gentle thruster for the Moon, using energy siphoned from the Earth's daily spin. For billions of years, our planet has been ever so slightly slowing its rotation in order to push its companion farther and farther away into the darkness of space. A slow, silent, and irreversible parting. The evidence for this process is written in stone, or more accurately, in ancient sediments. Certain sedimentary rocks, known as tidal rhythmites, preserve the daily, monthly, and yearly cycles of the tides in their fine layers, like pages in a book. By studying these ancient records, geologists can count how many days there were in a year, hundreds of millions of years ago. These records clearly show that in the distant past, the days were significantly shorter, and there were more of them in a single year. The Earth was spinning much faster, and the Moon was much closer. For example, about 620 million years ago, during a period known as the Ediacaran, the Earth's day was only about 21.9 hours long. A year contained over 400 of these shorter days. The Moon would have appeared significantly larger in the sky, and its proximity would have created much more powerful tides, with a faster and more dramatic daily rhythm. The world would have felt like a different place, with a quicker pulse, all because the Moon was closer and the Earth had not yet been slowed by billions of years of oceanic friction. The precision of modern science allows us to measure this effect in real time. Using laser ranging experiments, where beams of light are bounced off reflectors left on the Moon by the Apollo astronauts, scientists can measure the Earth-Moon distance with incredible accuracy. These measurements confirm, without a doubt, that the Moon is receding from us at a rate of approximately 3.8 centimeters per year. It is a slow and patient retreat, a speed comparable to the growth of a human fingernail, but over geological time, it adds up to a profound separation. This slow separation will not continue forever. The process of tidal breaking and lunar recession is self-limiting. As the moon gets farther away, its tidal influence on the Earth weakens. As the Earth's rotation slows, the mismatch in speeds between the planet's spin and the moon's orbit decreases. Eventually, in the far distant future, the Earth's rotation will slow down so much that one side of our planet will permanently face the moon, just as one side of the moon already permanently faces us. This state is called tidal locking. When this future state of mutual tidal locking is achieved, the day on Earth will be as long as the lunar month. The Earth's spin will perfectly match the moon's orbit. At this point, the tidal bulges will no longer be dragged ahead of the moon. They will be stationary relative to the Earth's surface, perfectly aligned with the moon, and the tidal friction will cease. The transfer of angular momentum will stop, and the moon will no longer recede. The Earth-Moon system will have reached its final, stable, and deeply quiet equilibrium. A silent, synchronized, and eternal dance. Let's re-examine this intricate chain of cause and effect, for it is a beautiful example of cosmic consequence. The moon's gravity creates tidal bulges. The Earth's fast rotation drags these bulges forward. This forward bulge pulls the moon ahead, transferring energy to it. The moon, in turn, pulls back on the bulge, slowing the Earth. This transfer of energy slows the Earth's spin, lengthening our day, and simultaneously pushes the moon into a higher, more distant orbit. It is a closed loop of feedback, a slow and patient exchange of momentum that has been shaping our world for its entire history. The energy source for this entire grand process is the rotational energy of the primordial Earth. When our planet first formed, it was spinning incredibly fast, perhaps with a day only a few hours long. All of the tidal evolution since then has been the slow, gradual dissipation of this initial spin energy. The oceans, acting as a brake lining, convert this rotational energy into gentle heat through friction, while the moon acts as a cosmic flywheel, absorbing the angular momentum and storing it in the vast potential energy of its ever-widening orbit. So when you look at the moon, you are looking at the recipient of Earth's ancient, youthful energy. Its silent, slow retreat is a direct consequence of the churning of our own oceans billions of years ago. And today, the distance between us is a measure of time, a clock that has been ticking since the very beginning. It is a profound connection, written not in light, but in the invisible ink of gravity and momentum, a shared history that has determined the length of our day and the position of the moon in our sky. Let us return to that central concept of angular momentum. It is a quantity of motion, a measure of an object's tendency to continue spinning. A spinning top has angular momentum. A planet orbiting a star has angular momentum, and a planet spinning on its own axis has angular momentum. The law of its conservation is one of the pillars of classical mechanics, a rule that brings a deep and satisfying order to the cosmos. It dictates that for every action there must be a reaction that perfectly preserves the total rotational state of a system. In the Earth-Moon system, the Earth's spin is a massive repository of this momentum. It is a spinning flywheel of unimaginable mass and speed. The moon's orbit is the second, smaller repository. The genius of the tidal interaction is that it provides a bridge between the two. The friction of the oceans is the conduit through which momentum can flow, slowly draining from the Earth's rapid spin and gently filling the vast, quiet reservoir of the moon's distant orbit. It is a balancing act on a planetary scale. This transfer is not an efficient process in terms of energy. Most of the rotational energy lost by the Earth is simply dissipated as heat in the oceans due to the friction between the water and the seabed. It is a tiny amount of warming, spread over the entire globe, completely insignificant compared to the energy we receive from the sun. Only a small fraction of the lost energy actually goes into lifting the moon into its higher orbit. But it is the angular momentum, not the energy, that is perfectly conserved and transferred. Consider the sheer inertia of the Earth's rotation. To slow down a spinning sphere weighing 6 sextillion tons is no small feat. It requires a steady, patient, and unopposed force acting over immense periods of time. The Moon, through the mechanism of the tides, provides that force. It is the perfect cosmic brake, applied gently and consistently for 4.5 billion years. Every breaking wave, every tidal current scouring a channel on the seafloor, is a tiny contribution to this immense project of slowing down a world. And on the other side of the transaction, consider the Moon. It receives this momentum, and the result is its slow, outward spiral. This is why the process is so stable. A moon that got pushed into a lower orbit would experience stronger tides, pushing it out again. A moon that somehow got pushed into a much higher orbit would experience weaker tides, and the rate of recession would slow. The system is self-regulating, a beautiful piece of natural engineering that has maintained the Earth-Moon partnership in a state of slow, predictable evolution for eons. This same process of tidal evolution occurs elsewhere in the solar system. The moons of Jupiter and Saturn are locked in complex tidal relationships with their parent planets, relationships that generate immense heat through friction, enough to create liquid water oceans beneath the icy shells of moons like Europa and Enceladus. The tides we experience on Earth are a gentle version of a universal process that can be powerful enough to make entire worlds habitable, a testament to the creative power of gravity and friction. The law of conservation of angular momentum provides a sense of profound order. It means that the Earth's day cannot lengthen without the Moon moving away. The two phenomena are inextricably linked, two sides of the same cosmic coin. One cannot happen without the other. This deep connection, this unbreakable link, is a source of intellectual calm. It reveals a universe that is not a series of disconnected events, but a single, vast, interconnected machine, where every change has a corresponding and equal consequence, even across hundreds of thousands of miles of empty space. So when we speak of the lengthening day, we are also, by necessity, speaking of the receding moon. The 1.8 milliseconds added to the day each century is the price paid for the 3.8 centimeters the moon gains in distance each year. It is a transaction, a cosmic payment of time in exchange for distance. This payment has been made every day, every year, for billions of years. A slow and steady accumulation of moments that has transformed the very nature of our planet's rhythm and its relationship with its celestial partner. Allow your mind to rest on this image of balance. The Earth, spinning down like a slowing top. The Moon, spiraling outwards like a stone released from a sling in ultra-slow motion. And the ocean, the vast, liquid interface between them, acting as the gear that connects these two motions, facilitating the transfer, ensuring that the books of cosmic momentum are always balanced. It is a system of profound elegance, running silently and perfectly in the background of our world, a deep and steadying rhythm beneath the chaos of daily life. This transfer of momentum also had a critical effect on the Moon itself, long ago. The Moon was once a molten body, spinning on its own axis. The Earth, being so much more massive, exerted a powerful tidal force on the Moon, creating body tides in its molten rock. This friction slowed the Moon's rotation down very quickly, geologically speaking, until its rotation was locked to its orbit. This is why we only ever see one face of the Moon. It was the first and most dramatic outcome of the tidal dance, a locking that happened billions of years in our past. So the tidal lock we see in the Moon is a preview of the Earth's own distant future. The Moon has already reached its equilibrium with respect to the Earth's pole. Its day is now the same length as its year, or in this case, its month. It has found its final, quiet resting state in this gravitational dance. Our own planet is still in the process of slowing, still slowly marching towards that same state of perfect synchronization, a journey that will take many billions of years more to complete, long after the Sun has changed its own nature. The concept of angular momentum allows us to look both forwards and backwards in time. We can calculate that in the distant past, the much closer Moon-created tides that were hundreds of times higher than they are today. Vast stretches of the early continents would have been flooded and exposed twice a day by these enormous tidal flows. This extreme environment may have been a critical factor in the early stages of life's evolution, a powerful engine for mixing the chemical ingredients of the primordial soup in shallow coastal pools. And looking forward, we can predict that slow, inevitable future. A future where the Earth is tidally locked to the Moon, and the day is over 1,000 hours long. The Moon would hang motionless in the sky for the inhabitants of one hemisphere, and be forever invisible to the other. The great engine of the tides would fall silent. It is a quiet, static, and profoundly different world, the logical endpoint of the slow, grinding process of tidal friction that we can feel today in the gentle rhythm of the sea. This grand timeline, from a fast-spinning past to a slow-spinning future, is a comforting thought. It places our own existence, our own brief moment in time, on a vast and understandable trajectory. We are living in one particular chapter of the Earth-Moon story, a chapter where the day is 24 hours long and the tides are gentle. It is a state of temporary, dynamic beauty, a fleeting moment in a multi-billion-year process of gradual and graceful change, all governed by the simple, unwavering law of the conservation of angular momentum. So let the idea of this great cosmic exchange be a final lullaby. The Earth gives a tiny piece of its spin to the Moon. The Moon accepts this gift and uses it to move a little farther away. This has been happening since the beginning, and it will continue long after we are gone. It is a constant, a reliable feature of our world, a testament to the fact that the universe is bound by laws of balance and consequence. There is no need to hold on to this thought. Simply let it be, a quiet background hum of order and predictability as you drift deeper into sleep. Let's focus for a moment on the simple, tangible fact of the Moon's retreat. 3.8 centimeters per year. It is a distance you can easily measure with your hands. It feels small, almost trivial. And yet, this tiny annual separation is the cumulative result of a planet's worth of water sloshing against the seabed, a friction engine of continental proportions. It is a beautiful example of how a very small persistent effect can lead to enormous changes when given the luxury of deep geological time. The universe is built on such patient, incremental processes. Every year, the Moon's orbit expands by this small amount. Its journey around the Earth becomes slightly longer, not just in distance, but in time. This is the great paradox of orbital mechanics. By speeding up due to the tidal pull, the Moon moves to a higher orbit where its overall orbital period is actually longer. It moves faster, but has farther to go, so the journey takes more time. It is a subtle but important distinction, showing how an injection of energy can lead to a more languid, stretched-out orbital dance. This recession means that total solar eclipses are a temporary phenomenon in the Earth's long history. A total solar eclipse occurs because, by a remarkable coincidence, the Moon is currently at just the right distance from Earth to appear the same size as the much larger, much more distant Sun. In the distant past, the closer Moon would have easily and completely blocked out the Sun. In the distant future, the receding Moon will appear too small in the sky to ever fully cover the Sun's disk. We live in a special astronomical epoch, a brief window of cosmic geometry. Imagine that future sky. The Moon will be a noticeably smaller, less brilliant disk of light. Its gravitational influence, and thus the tides, will be weaker. It will be a more distant, more subtle companion to our world. Its slow retreat is gradually diminishing its presence in our sky and its physical effect on our planet. We are privileged to live at a time when the Moon is still close enough to be a major character in Earth's story, creating spectacular eclipses and driving the powerful ocean tides that have shaped our coastlines and ecosystems. The 3.8 centimeter retreat is an average. The Moon's orbit is not a perfect circle. It is a slight ellipse. Its recession rate varies slightly depending on where it is in its orbit, and it is also influenced by other, much smaller factors like the gravitational pull of other planets. But the average holds true, a steady trend measured over decades. It is a reliable beat in the slow rhythm of the solar system, a testament to the precision with which we can now observe the cosmos, turning abstract theories into measurable, centimeter-scale facts. This slow retreat is the moon's response to Earth's hospitality, in a way. The friction in our oceans is a gift of momentum, a gift that the moon must accept, and in accepting it, it must move away. It is a slow, unavoidable parting of ways, dictated not by choice, but by the fundamental laws of physics. It is a relationship that is constantly, slowly, and predictably evolving, moving from an ancient, close, and violent embrace towards a distant, quiet, and stable partnership. A cosmic story of growing up and moving apart. Do not feel any sense of loss in this recession. It is a process so slow as to be utterly irrelevant on a human timescale, or even on the timescale of our entire species. For all of human history, the moon has been, for all practical purposes, at the same distance. It will remain our constant, familiar companion for countless generations to come. Knowing of its slow retreat is not a cause for alarm, but a source of deeper perspective, a way of understanding our place in the long, slow, unfolding story of our world. The energy required to lift the moon by 3.8 centimeters each year against Earth's gravity is considerable. It is equivalent to the output of several large power plants running continuously. All of that energy is being drawn directly from the Earth's rotation, a silent and massive transfer of power that occurs every second of every day. The tides are not just a movement of water, they are a planetary-scale energy transmission system, converting the kinetic energy of a spinning world into the potential energy of a rising moon. This recession has been happening for at least 4 billion years. If you multiply 3.8 centimeters by 4 billion years, you get a vast distance, one that would place the moon impossibly close to the Earth in the beginning. This tells us that the rate of recession has not been constant. In the past, when the moon was closer and the Earth was spinning faster, the tides were stronger, the friction was greater, and the rate of recession was much, much faster. The retreat has been slowing down as the system loses energy and approaches equilibrium. Let the image of this slow, outward spiral be a gentle anchor for your mind. It is not a frantic escape, but a graceful, patient expansion of an orbit. It is the result of a perfectly balanced exchange of momentum, a dance choreographed by the laws of gravity. The moon is not leaving us, so much as it is ascending to its final, stable position in the Earth-Moon system. It is a journey that takes billions of years, and we are simply witnesses to one small step along that grand cosmic path. Now, let's turn our attention back to our own world, to the other side of this great transaction, the lengthening of the day. It is a subtle change, an extra millisecond or two added to the day every century. For your entire life, the day has been, to all human perception, exactly 24 hours long. But the Earth beneath you is an imperfect clock, a clock that has been slowly winding down since its creation, and the tides are the mechanism responsible for its gradual loss of time. This slowing is not perfectly smooth. The Earth's rotation is subject to other, smaller fluctuations. The movement of molten rock in the planet's core, the melting of ice caps, and even large-scale weather patterns can slightly speed up or slow down the Earth's spin on a short-term basis. But underneath all this noise, the relentless, one-way trend of tidal breaking continues, a steady and irreversible march towards a longer day. It is the deep, fundamental rhythm, while these other effects are just temporary variations on the theme. To maintain our precise system of timekeeping, we occasionally have to add a leap second to our clocks. This small adjustment is a direct acknowledgement that our atomic clocks, which are incredibly stable, are running slightly faster than the slowing rotation of our own planet. The leap second is a bridge between the perfect, abstract time of physics and the messy, beautiful, astronomical time of our spinning world. It is a tangible consequence of the moon's distant gravitational pull on our oceans. Imagine the world of the dinosaurs, some 100 million years ago. The day was closer to 23 hours long. This would have had a subtle but real effect on climate and the daily cycles of life. The sun would have seemed to move slightly faster across the sky. The patterns of day and night, of heating and cooling, would have been accelerated. The world that those creatures inhabited was a faster-paced version of our own, all because the moon was closer and less of the Earth's primordial spin had been drained away by the patient work of the tides. The very concept of a day is not a fundamental constant of the universe, but a planetary variable, a number that has been evolving for the entire history of our world. We just happen to be living at the moment when that number is 24 hours. This realization helps to decenter our own experience and place it in a much grander context. Our familiar rhythms are not absolute. They are a product of a specific astronomical configuration, a snapshot in the very long and slow-moving film of our planet's history. This slowing of the Earth is a form of aging. Just as a living being slows with age, the planet itself is slowly losing its youthful rotational vigor. It is a natural, inevitable process of maturation for a planet with a large moon. This process brings stability. A slower rotation can lead to less extreme weather patterns. The journey towards tidal lock is a journey towards a quieter, more stable, and more predictable state. It is a calming thought that the universe, left to its own devices, often trends towards states of lower energy and greater peace. Let the thought of this slowing rotation be a comfort as you prepare for sleep. Feel the world turning beneath you, but feel it as a slow, majestic, and reliable motion. It is not a frantic spin, but a graceful and slowing waltz. You are safe on this massive, spinning sphere, held fast by its gravity as it continues its ancient and steady rhythm, a rhythm that is itself slowly, calmly, and predictably changing, guided by the gentle, persistent influence of its moon. The interconnectedness is perfect. The slowing day and the receding moon are not two separate stories. They are one story, told from two different perspectives. One is the story of time. The other is the story of space. But they are driven by the same engine, the tidal friction in our oceans. And they are bound by the same law, the conservation of angular momentum. Understanding one is to understand the other. It is a single, unified, and deeply elegant piece of cosmic clockwork. As you close your eyes, you can perhaps feel this great, slow turning of the world. It is the most constant motion in your life, the backdrop to every moment. And this motion is connected, through the liquid medium of the ocean and the invisible force of gravity, to the moon in the sky. You are part of a system, a dynamic and beautiful partnership between world and moon, a partnership that has shaped the very rhythm of life on Earth, and will continue its slow, evolutionary dance for ages to come. We have now explored the grand, long-term consequences of the tides. But the story has one more layer of complexity. The real world is not a simple theoretical model. The oceans are not a uniform layer of water, and their interaction with the land is not straightforward. The actual behavior of the tides, as they navigate the complex geography of our planet, creates strange and wonderful patterns, turning our simple two-bulge model into a much more intricate and fascinating reality. This is where the theory meets the beautiful chaos of the real world. The simple model of two tidal bulges through which a smooth Earth rotates is a powerful tool for understanding the fundamental forces at play. But our world is not a smooth, water-covered marble. It is a world of continents, of vast land masses that act as immense barriers to the free movement of this planetary scale wave. The tidal bulges cannot simply sweep unimpeded across the globe. Instead, they are forced into the great ocean basins, the Pacific, the Atlantic, the Indian, where they are trapped and must behave in a much more complex and fascinating manner. The story of the tides is not one of a simple wave, but of water sloshing within these immense, irregularly shaped containers. Within these basins, another force comes into play, a subtle but crucial consequence of living on a spinning sphere, the Coriolis effect. This is the same effect that deflects the paths of winds and ocean currents. creating the great circulating gyres in our oceans and the spiral patterns of hurricanes. On a rotating planet, any object moving over a long distance appears to be deflected from a straight path. In the northern hemisphere, this deflection is to the right, and in the southern hemisphere, it is to the left. This gentle, persistent turning force is the key to organizing the chaotic sloshing of the tides into a surprisingly elegant pattern. Imagine the tidal crest, the high tide, trying to move across an ocean basin. As it moves, the Coriolis effect continuously deflects it. In the northern hemisphere, it is pushed to the right. The wave tries to move north, it is pushed east. It tries to move east, it is pushed south. It tries to move south, it is pushed west. The end result of this constant deflection is that the tidal wave does not travel in a straight line at all. Instead, it is forced to pivot around a central point in a vast, counterclockwise rotation. This is the true nature of the tide in an enclosed basin. At the very center of this great rotation, there is a unique location where these forces all balance out. This is a place where the crest of the high tide rotates around, but the point itself experiences no change in water level at all. It is a point of zero tide. This remarkable location is called an amphidromic point, from the Greek words amphi, around, and dromos, running. It is a tranquil eye in the center of a vast, slow-moving tidal storm, a node of stillness around which the oceanic rhythm of an entire basin revolves. Our planet's oceans contain several of these mysterious, calm hubs. From each amphidromic point, the tidal wave radiates outwards, like the spokes of a wheel. These radiating lines are called cotidal lines, and they connect all the locations that experience high tide at the same time. As the tidal wave rotates around the amphidromic point, a process that typically takes about 12 hours and 25 minutes, this spoke of high tide sweeps around the basin. So instead of a bulge moving east to west, the reality is a series of vast rotating waves, each spinning around its own pivot point, their edges sweeping across the coastlines to deliver the high and low tides. This is a profound shift in our mental model. We must replace the image of a simple planet-girdling wave with a mosaic of enormous, interlocking, rotary waves. Each ocean basin has its own system of amphidromic points, its own unique tidal dance. The North Atlantic, for instance, has a large amphidromic system that rotates counterclockwise. This is why high tide does not arrive in Europe and North America at the same time. Instead, the wave crest sweeps around, arriving in different locations at different predictable hours, like a great, slow, cosmic clock hand making its rounds. The amplitude of the tide, the difference between high and low water, is also governed by this system. At the amphidromic point itself, the tidal range is zero. As you move farther away from this central point, the amplitude of the tide increases. The greatest tidal ranges are found at the farthest edges of the basin, often where the wave is funneled into a bay or channel. So a map of the tides in an ocean basin would look like a series of concentric circles around the amphidromic point, with the tidal height increasing with each outward ring. The existence of these amphidromic systems explains why the timing and height of tides are so intensely local. Your experience of the tide depends entirely on where you are in relation to these vast rotating systems. It depends on your distance from the amphidromic point and on the particular time that the rotating crest of the wave happens to sweep past your section of the coast. The beautiful, simple two-bulge theory provides the energy, but the complex choreography of the continents and the Coriolis effect determines the final performance. This also explains why the simple rule of 2 high tides a day is not universal. The timing of the Earth's rotation and the natural period of these rotating waves leads to different patterns. Most places experience the familiar semi-diurnal tide, with 2 high and 2 low tides of roughly equal height each day. But in some parts of the world, like the Gulf of Mexico, the basin's shape and size are such that it only allows for one dominant tidal wave to circulate each day. This results in a diurnal tide, with only one high and one low tide per day. In other places, particularly along the Pacific coast of North America, the systems are even more complex. The basin supports two separate amphidromic systems, one diurnal and one semidiurnal. The interaction of these two different rotating waves creates what is known as a mixed tide. In this pattern, there are still two high tides and two low tides each day, but their heights are unequal. You will experience a high tide, followed by a low high tide, and a low tide followed by a high low tide. A complex and fascinating rhythm born from the overlapping of two different tidal frequencies. So the geography of our planet acts as a filter. The moon and sun provide a rich spectrum of gravitational forcing, with cycles of 12 hours, 24 hours, and more. Each ocean basin, with its unique shape and depth, has a natural resonance, a frequency at which it wants to slosh back and forth. If the gravitational forcing matches the basin's natural resonance, the tides can be amplified to extraordinary heights. This is the secret behind the world's most dramatic tides, like those in the Bay of Fundy. It is a case of perfect cosmic and geographic alignment. The Bay of Fundy in eastern Canada has a natural sloshing period, or seiche, of about 13 hours. The moon's semidiurnal tidal forcing has a period of about 12 hours and 25 minutes. These two numbers are incredibly close. The result is a near-perfect resonance. Each time the Atlantic's tidal crest arrives at the mouth of the bay, it gives the water a push, just as it is naturally sloshing in the same direction. This repeated, synchronized pushing builds the wave to an incredible height, resulting in tidal ranges that can exceed 50 feet, the highest on Earth. There is another layer to this story, a tide that is completely invisible to us on the surface. The ocean is not a uniform body of water. It is stratified into layers of different temperatures and salinities, and therefore different densities. There is a boundary, known as a pycnocline, between the warmer, lighter surface water and the colder, denser deep water. Just as the moon creates a tide on the ocean's surface, it also creates a tide along this internal boundary. These are known as internal tides. These internal waves can be enormous, with heights of hundreds of feet, far larger than the surface tides that create them. But because they are happening deep within the ocean, and the density difference between the layers is small, they move very slowly and have no visible effect at the surface. They are silent, slow-motion giants, moving through the deep ocean. They are generated when the surface tide flows over underwater mountain ranges and ridges, disturbing the deep layers of water and creating these immense, slow internal ripples. The energy carried by these internal tides is immense, and their breaking plays a crucial role in mixing the ocean's waters. This vertical mixing is vital for the planet's climate system, as it helps to transport heat from the surface into the deep ocean and brings vital nutrients from the depths up to the sunlit surface where they can support marine life. The gentle, familiar tide we see on the coast is therefore just the tip of the iceberg, the surface expression of a much larger system of energy transfer that stirs the ocean from top to bottom, driven by the distant pull of the moon. Finally, we must acknowledge that the tides are not a perfectly isolated system. They are influenced by the weather. A strong onshore wind can pile water up against the coast, making a high tide even higher. Conversely, a strong offshore wind can push water away, making a low tide even lower. More dramatically, a storm surge, caused by the low atmospheric pressure and high winds of a hurricane or major storm, can create a sudden and dangerous rise in sea level that can be devastating when it coincides with a naturally high spring tide. But these weather effects are temporary and unpredictable. They are noise superimposed on the deep, reliable, and perfectly predictable signal of the astronomical tides. Long after the storm has passed and the winds have died down, the tide will continue its faithful rhythm, rising and falling in perfect time with the celestial clockwork of the sun, earth, and moon. This predictability is one of the most reassuring aspects of the tides. In a world that can often feel chaotic, the tides are a symbol of a deep and unwavering cosmic order. And so our quiet journey through the science of the tides is drawing to a close. We have traveled from the fundamental law of universal gravitation to the subtle concept of differential forces that stretch our world. We have seen how these forces create two opposing bulges in our oceans, and how the Earth's rapid rotation through these bulges gives us the familiar rhythm of the daily tides. We have witnessed a story of immense power, moving trillions of tons of water with a silent, invisible hand. We have explored the supporting role of the sun, whose own tidal forces sometimes align with the moon's to create the great spring tides, and sometimes work against them to create the gentle neap tides. This monthly cycle is a direct reflection of the orbital geometry of our corner of the solar system, a rhythm of alignment and opposition played out in the waters of our own world. A beautiful and direct connection between the familiar lapping of waves and the grand, celestial dance happening far above our heads. We have journeyed through deep time, discovering the profound consequences of tidal friction. We learned how this gentle break on the Earth's rotation has been slowly lengthening our day for billions of years, and how the conserved angular momentum from this process has been steadily pushing our moon farther and farther away. A slow and irreversible exchange, a transaction of time for distance that has fundamentally shaped the past and the future of the Earth-Moon system. A story of a slow, cosmic parting. And finally, we have seen how this simple, elegant theory meets the complex reality of our world. We saw how the continents block the tidal wave, and how the Earth's own spin twists it into vast, rotating systems called amphidromic waves. We saw how these systems, with their calm, tideless centers, are what truly deliver the tides to our shores, creating the rich variety of diurnal, semi-diurnal, and mixed tides that we observe across the globe. A final, beautiful layer of complexity, turning a simple model into a living, breathing, and wonderfully intricate reality. The science of the tides is a perfect subject for the end of the day. It is complex enough to gently occupy the mind, preventing it from straying to the anxieties of the day. But it is also a story of immense calm, of deep rhythms, and of a profound and reassuring order. It is a story of balance, of action and reaction, of cycles and epicycles. It is a story that connects the ground beneath our feet to the most distant object in our night sky, a story of an invisible, unbreakable bond. Let this knowledge settle within you now, not as a set of facts to be remembered, but as a feeling of connection to a vast, orderly, and deeply beautiful universe. A feeling of reassurance that even the most powerful forces can result in gentle, predictable rhythms. A feeling of being part of a system that is far older, far larger, and far slower than our own brief and busy lives. There is a deep comfort in this perspective, a release from the urgency of the immediate. The tide is now an old friend, its mysteries revealed. You understand the gravitational whisper of the moon that calls it into being. You understand the twin bulges, the one pulled and the one left behind. You understand the monthly rhythm of the spring and neap tides, and the eons-long story of the slowing Earth and the receding moon. You understand the great, silent, spinning waves in our oceans. There is nothing left to figure out. There is only the gentle rhythm, the intellectual hum of understanding. Your mind has been on a long journey tonight. It has traveled across space and through time. It has explored the laws of physics and the geography of the planet. It has done its work. And now, it is time for it to rest. Just as the ocean finds its moment of slack tide, the calm pause between the ebb and the flow, so too can your mind now find its own point of stillness. A quiet equilibrium where thoughts cease to rush in and out, and a deep, profound calm is allowed to settle. Release the details now. Let the specifics of amphidromic points and angular momentum drift away. They have served their purpose. What remains is the essence of the story, the gentle, rhythmic, and predictable connection between our world and the moon. Allow this feeling of serene order to be the soft surface upon which you rest your consciousness. There is a deep peace in knowing how the world works, and an even deeper peace in letting that knowledge dissolve into a simple feeling of wonder. Your breathing is now your only tide. Feel the gentle rise and fall of your own body, a simple biological rhythm that has been with you your entire life. It is your own personal, constant connection to the great rhythms of the universe. Each breath is an echo of the ocean's tide, a reminder of the cycles that govern all things. Let this simple, familiar motion be your final anchor, the last gentle sensation you are aware of as you drift away from the shores of wakefulness. You are now floating in a quiet space, a space of intellectual comfort and deep relaxation. The story is complete. The universe is in its place, moving with silent, majestic grace. The moon continues its orbit, the earth continues its slow rotation, the oceans continue their ceaseless, gentle breathing. All is as it should be. There is nothing for you to do, nothing for you to solve. You have only to surrender to the pull of sleep, a force as natural and as gentle as gravity itself. Thank you for joining us here at Sleep Science Studio. It has been a pleasure to be your guide on this quiet exploration of the tides. I hope our journey has provided a soft place for your mind to rest, and that the intricate dance of the cosmos has become a soothing lullaby. May the deep, predictable rhythms of the universe echo in your own deep and restorative rest. May your sleep be as peaceful and as profound as the silent, starlit ocean at high tide.